Hello, welcome to another video, Unit 3, Chemistry 1050. This is a video that is going to deal with solutions and solubility. So we've been looking at, just in previous videos, we've been looking at reactions and equations, and here's a little summary of where we've been in former videos, and now I'm going to get into what are called precipitation reactions. We've dealt with synthesis, decomposition, single and double displacement replacement interchangeably. There's also a video on combustion and other types of combustion, which is a type of oxidation reduction reaction. So this video is going to deal with precipitation reactions. So anytime we see in a reaction that a solid or semi-solid residue or basically a non-aqueous product is formed, including even a pure liquid. So let's look at what soluble means. We're looking at that we have, a solute basically that is dissolving in that particular solvent. So it's insoluble. A compound we would say is insoluble if it doesn't dissolve in the liquid. So an aqueous solution, though, is going to be a mixture, homogeneous, looking the same throughout. Think about Kool-Aid, think about sugar or salt dissolved in water when you can't see the particles. That would be an aqueous solution. And so when we have an ionic compound, such as NaCl, such as your typical table salt, because there's ions in those compounds, they will typically dissociate into their ions when they're in water, because water has slightly positive and slightly negative ends as well. So the like attracts like. So here's that basic example. Here's a nice little diagram. We see Na plus ions and chloride, so sodium ions and chloride ions are floating around. The NaCl solid dissociates when it's in water. So this forms an NaCl or salt solution. So ionic compounds completely dissociate, and the ones that completely dissociate, because there are some that only slightly, but most completely dissociate or break apart, if you will. These are called strong electrolytes, and the word electrolyte gives us the hint. Hopefully you're thinking electricity, and that is in fact the case, because if we have an ionic compound that dissociates in water, and water, a pure liquid, and forms an NaCl aqueous solution, if we were to actually set up this circuit, the ions in the sodium chloride solution actually will conduct electricity, and we would see a light bulb light up if we had this set up with the two electrodes in the battery. So ions conduct. So a little bit more about aqueous solutions. AgNO3, for example, silver nitrate. If it's AQ, this is what's important, it does not contain any AgNO3 units together. They split apart. So when we have positive and negative, we've got splitting apart. If it's aqueous, only if it's aqueous. All right, so what that means is that in this beaker of water, we only have Ag plus floating around and NO3 negative floating around amongst the H2O molecules. There are no AgNO3 complete units. This is a strong electrolyte, so we've got ions floating around. It would conduct electricity if we were to set that surface up. So that NO3 is NO3, that nitrate ion is called a polyatomic, poly meaning many, atomic atoms, many atoms joined together sharing a charge. That NO3 negative never dissociates. Just a little note there. So, as I said, most ionic compounds dissolve, but not all. Here's an example of one that remains intact. Look at this silver chloride. It's an ionic compound, but notice how its three-dimensional crystal lattice, typical of ionic compounds, stays intact. And so AgClS will remain like this in water. And you might say, well, how are you supposed to know that? You're not supposed to memorize that at all. If we were to look up how silver ion combines with chloride ion in that table 4.1, the solubility table that I've made reference to in other videos, you will see that it would say insoluble, which means we put an S here. And my table is similar. Yours is on page 157. This is very similar, not identical, just because it was a nicer image to use in the presentation here. And so, for example, let's go look at that Ag All right, so compounds containing the following ions are mostly soluble, meaning these compounds that contain these would be mostly soluble. So we'd have aqueous, and the compounds containing here are mostly insoluble. So so if you see here some exceptions, when either of these ones, so when hydroxide, OH minus or S2 minus, a sulfide ion, if either of those are paired with any of these ones here, they would be soluble, so they'd be an AQ. But if sulfide pairs with any of these column 2 metals, the compounds will also be soluble. All right, so these we're going to use this table to look at how the pairings go. And so let's see, we've got nitrate here, and these are mostly soluble, meaning like, for example, K with NO3, like these column 1s. So if we had KNO3, NaNO3, NH4NO3, LiNO3, those would be soluble. But look at the exception. When any of these pairs with, look at that, there is the silver, the Ag+. So the silver ion with the nitrate ion would be considered insoluble, so you would write an S in the subscript. So you look at your table to figure that out. It's never to be memorized. So when that solid is formed, either it stays intact, or essentially if it's made from two previously aqueous solutions, if we see this solid, or even let's call it a semi-gelatin-like almost, if you see that, like for example here in lead-2 iodide, see that solid there? That is that yellow substance that we see appearing from two colorless aqueous solutions. Then all of a sudden we have this lead-2 iodide and then potassium nitrate. And if you were to look up in your table, you'll see that when lead goes with iodide, we will have a precipitate. So here's iodide. Notice how it says if it pairs with lead, it's insoluble. So that's how we know that yellow that we see is in fact this particular one here. So this is nice to show you what's happening in the lab, and this is more of that model type diagram. So we've got potassium iodide and lead-2 nitrate here coming together, and then when they come together in solution, notice what happens. We've got rearranging going on here, and potassium nitrate is then still floating around as the two separate ions, and then the lead-2 iodide forms, and there it is. So basically a precipitation reaction is when we have a solid called a precipitate after mixing two aqueous ones, which is in fact different than what I had said here. Yes, it's a solid, but this is just me looking at the individual ionic solid itself and the fact that it doesn't. So this would be like if I said, if we put lead-2 iodide in a beaker, what would happen? You'd look up that it's insoluble and you'd say, well, it would remain intact. Whereas this one is the production of, or the result of, two aqueous reactants. So how do we write these equations? So if all the potential products are soluble, we would say no reaction occurs. And we've seen this in former videos, for example, the one about double displacement reactions. If two aqueous solutions come together and form two more aqueous ones, we'd say no reaction. So we have to check that table 4.1 for solubility. So here's an example. Write an equation that occurs between when solutions of. So I have that in green to indicate that if it says when solutions of, what we're looking at there is, just want to highlight that, is that if solutions of means these two beginning reactants here, sodium carbonate, copper 2 chloride, are aqueous when they begin, and then what we do is we do a double displacement reaction. We'll see NaCl form and copper 2 carbonate, and when you look it up in the table, you will notice that this one has the solid. So here are two more for you to try. I'm just going to leave those with you. When we go a little further than this, I want to look at the next bit here called molecular and complete ionic equations. So what this is it's taking that precipitation reaction into a little bit more detail. So the molecular equation is just, here's the double displacement reaction, like what I just did with you with the lead-2 iodide, or what was it here? It was the copper 2 carbonate. And so it's taking that precipitation reaction into more detail. we can be asked to show exactly what's happening. We say that shows the molecular compound equation. Then what we do is we can take it further by taking all of the aqueous compounds and we split them up into their ions. Okay? But the one that is the solid in the beginning remains solid, because a complete ionic equation shows all the ions that are floating around in those beakers. Think of it as this stage right here, showing what's going on in all the beakers before and after. This is what this middle equation is showing us. So when we mix these two solutions together, we'll have silver ions floating around, nitrate ions floating around, sodium ions, chloride ions, etc. But in that beaker, this silver chloride will stay together. Now, this is the last part here in this procedure of writing molecular and complete ionic. The whole purpose is to figure out what the net reaction is. A good analogy here would be like when you make your gross salary, there's going to be several deductions. So that's kind of like what this first and or second step are, showing everything that you have. Take all the deductions off. The net would be like really what you care about. What ends up in your bank account after all the deductions, that net paycheck. This is the net ionic equation, shows us really who the key players are. So it's the silver ions, the chloride ions that are forming that precipitate that you see. So the ones that are not in the net are called spectator ions. So that would be the nitrate right here and the sodium. Those two are spectating, if you will. They are not participating in forming that solid. So the only compounds that we separate will be the aqueous ones, and we never separate a solid, liquid, or gas. Okay, we're only looking at the aqueous ones. So here's another example. This one shows the molecular, so I just said same as above. The ionic, I take all of the aqueous ones, I split them up. So if it's 2HBr, there are 2 H plus ions and 2 Br minus ions. And how do I figure out those charges? Column 7, column 1. So I'm using that knowledge. So CaOH2, be careful here. It's only 1 calcium ion and it's 2 hydroxide ions. And these can be looked up in the tables in your book. This is in column 2, so it's a charge of 2 plus. Now, notice I have this highlighted as red. We do not split up pure liquids, only the aqueous ones. Aqueous compounds. So notice that the net is how do we form that one that is not aqueous, and water comes from hydroxide and hydrogen. So this net one is looking at how did this one get formed. Okay, and I'm going to leave you with this example here. So I'm going to conclude that part of the video, this video now I should say, and I'm going to do one more video on the last topic in the unit. So thanks for watching. Please post any questions in the Q&A.